Hola, Maga. Hola, Claudio.
Hola.
So I guess while we're waiting for 2 or 3 more people to show up, so what do people think about the 12th through the 16th? Is that doable for the test, the exam?
Yeah, we were actually, we made a little like over test we had, like everyone, and so far that week is like the best one. We talked about the 15th. That's the only day we said like, hey, everyone can be safe. We haven't talked about the other days because they have a presentation of variable stars on Monday 12th. So we thought like maybe they would need a couple of days. But that's it. I think that Roy was the only one left to say if he could the 15 also. But that was a day most of us could.
Yeah, I don't know if it's been communicated, but the Trabajo de Investigación, the presentations are going to be the 19th, 20th, and 21st.
Yeah.
Okay. Monday, Tuesday, Wednesday. So I assume you want to keep those free. And also I need like at least a week to probably grade, and then I have to submit the grades by the 27th of July. So
yeah,
that's kind of why that week needs, it should happen kind of that week. So if you want to go ahead and fill out the poll of what time would be best that I just sent out, if you want to just focus on the 15th, that's fine.
okay.
But that way we can narrow in on a 3-hour range that hopefully is okay for everybody. Okay, good. Let's see, anything else? I still owe you homework, so I'm about to do it. I was on attack all week last week, so telescope allocation committee, so I was reading stuff and yeah. Okay, so I plan to send out at least a few of the homework about this later tonight. So 6 and 7, and then probably 8 will come tomorrow. Okay, so with that, this is the last class, and so we saved the toughest thing for last, or at least maybe not the toughest, but the most annoying. It isn't actually the toughest necessarily, but in terms of math. Okay, so let me bring this up. Oops, come on. Go. All right, so dust is sort of complex molecules, and they of course make things a little bit complicated. And so when we talk about dust, really what we're talking about are molecules that are complex enough that they kind of end up being, well, sort of considered macroscopic particles. And so they typically will have sizes of the order of microns. And so they're made up of various different components. They could be ices, they could be sort of carbon-based things, they could be silicate-based or iron-based. Those are kind of the typical components. And so, yeah, in general, they're sort of composed of dielectric or refractory material. And the properties of them are, I guess, let's call it an active area of research. So it's just not very well understood physics, and this is partly because it's not simple quantum mechanics, but it's bordering on sort of solid state physics slash molecular chemistry slash whatever. And so almost a good fraction of what we've been doing, sort of know about dust is all from empirical measurements, and sort of an imprecise estimate of what the composition of the dust grains is, an imprecise estimate of what the physical properties are, and so forth. And so, there are two ways of going about measuring those things. And one is by looking at the light it takes away from background sources, right, stars or quasars or whatever. And then the other is looking at the emission properties of the dust itself. And of course, that's tricky because a lot of the dust emission comes in the far infrared, and you can't observe that from the ground, right? And so we really rely on space telescopes, and in particular, these to date have not been necessarily the biggest telescopes with really high sort of fine resolution, high spectral quality, and so forth, due to detector limitations, monetary limitations, what have you. And so then, we have sort of tentative explanations of sort of the observed phenomena, and then people have tried to reproduce grains in the laboratory in sort of the conditions that would be similar to outer space, but there are a lot of processes involved. And this is particularly because you can throw the molecules into your vacuum and look at how they interact, but it's not the same environment because you don't have cosmic rays, you don't have a high UV radiation field, you don't necessarily have the same the total number and parts of elements that you might need, and so it's a complex thing to get right. And then, of course, there are differences depending on the environment. If you're near a star, if you're in the intergalactic medium, so we can measure something like dielectric constants for pure water or simple ices, but we can't necessarily measure those same things for what's known as dirty ices. So where you have maybe 99% is sort of pure water ice or carbon dioxide ice, but then you have impurities in there, and those impurities actually affect the properties, and that's tricky to know. And then you have that these ices are bombarded by cosmic rays, and that can eat away at the interior portions of it, and so it's not uniform, and that of course also has implications. So generally, the way we would, as I mentioned, the way we would interact with these dust grains and understand their properties is by looking at the interaction with starlight. And so you can infer the dust along the line of sight via what it does to the starlight that's passing through. Another way is direct emission from the dust grains, and then another way is looking at depletion of refractory elements in the interstellar gas. And so here, on the first one, where we can look at the total and the wavelength-dependent extinction through different mediums, and we can look at the combination of absorption and scattering. So you can see, absorption along the line of sight, but you can also see how it scatters light into our direction from other lines of sight. And so a couple examples of this are the absorption of starlight by silicate bands or ice bands, for instance. And then, of course, there's a reflection of starlight by dusty clouds, these reflection nebulae, and you can look at the polarization of the light that's either been scattered or through the passage of regions that have aligned dust grains, and so they can preferentially sort of polarize the light in that way. From the direct emission, you have thermal continuum from the dust grains, And this typically emerges in the mid-infrared to far infrared. And this emission, well, it can be sort of in relation to a local radiation field, but you can also have non-equilibrium heating of dust grains that might emit in the near infrared or mid-infrared. These are sometimes known as cell grain grains. And so the size of the grain it kind of tells you where it's going to emit and also where it can exist. And so big grains generally will get broken up by high energetic photons. And so they won't be too close to very energetic regions like AGN or young stars. Then you have inner IR emission bands. These could be silicates or PAH features. Well, I'll go through more of this in detail. I'm just kind of introducing it. And the brightest of these are identified, but then there are many that are still not really well known. And then you actually in the radio band, you can have grains that rotate, and the same way with molecules that are rotating in emission lines, with rotating grains, because there's a lot more dimensionality to it. They generally don't emit in lines, but in kind of regions of wavelength. And these are sort of more poorly known, I would say. They've only really been recently discovered in the last sort of 20 or 30 years. So, in terms of pictures, we have, these are very dark clouds where you have really strong distinction of the background stars in the optical bands. And then when you go to, say, the near infrared, you can start to see through them, right? And this is why, of course, we use the near infrared bands to study the galactic center, the bulge, et cetera, because they're much less affected by extinction. And then you have something like the Pleiades, where you have this classic sort of star forming region, and you can see that you have these halos of scattered emission that are coming from dust grains in the sort of larger star forming or star cluster environment. And so, as I mentioned, this is really still an active area of research, and as we launch new or sort of explore new regions of wavelength coverage, we learn more about this. And just to give you an idea of the importance of dust, so the dust ratio in the Milky Way is 100 to 1, right? Or the gas to dust ratio. So for 100 particles of gas, there's 1 particle of dust. And then the ISM makes up about 10% of the total baryonic mass of the galaxy. And so dust grains by mass, by total mass, are about 0.1%. Cut out. How long did I drop out?
Just a few seconds.
Okay. It just, for some reason, it reloaded. Okay. I lost it. Here we go. Okay. Right. So hopefully I was still on this one. So as I said, dust is not a very large component. It's 100 to 1 in terms of gas to dust ratio, and then it's 0.1% of the total mass. And then if you compare this to the effect it has, dust can absorb something like 30 to 50% of starlight emitted from the galaxy, and then re-radiated in the far infrared. And so you're talking about basically 0.1% of the baryons are ultimately responsible for how exactly almost half of the bolometric luminosity of the galaxy is seen, right? So it's taking the UV and optical radiation and it's reprocessing it and putting it out in the infrared. And so it's very fundamentally important. So the other really key factor for dust grains is that they're the site of most molecule formation. And so, essentially they're responsible for most of the molecular hydrogen in the ISM. And most of the molecular chemistry form is happening on the dust grain. So you have individual elements that collect onto the dust grains, then they actually are close enough so they can bond, and then they pop off. And so they're very important in this respect. And so planet formation, for instance, is believed to begin only when dust grains start forming in the protostellar disk. And so they kind of lead to the larger scale planetesimals and eventually the planets. So some of this has come from Restrain's annual review article and his lectures. So if you want to learn more, you can go and get those. So the way we would typically characterize dust in the early days when we were mostly observing with the optical is, was initially sort of discovered by the fact that it was extinguishing starlight along the line of sight. And so in early observations, people noted that dark clouds had fewer stars, and they were affecting the colors of the stars as well. And so for the very simple case of a distant star, as that light is passing through the interstellar medium, we can just develop an effective sort of equation of radiative transfer. And so it looks something like that. And so we have our intrinsic spectrum, we have our observed spectrum, and then the effect of the dust grains is from this extinction term here, this optical depth, where this is the line of sight optical depth, and it's a function of wavelength. And so this particular form assumes that it's all absorbed, no scattering. And so if you want to have a scatter component, we'll go back to the lectures, the early lectures, and put in a scatter component too. But nonetheless, this can these formal basis of an understanding. So there's no source function here at all. And so all the extinction is basically from what we call a dust grain geometry. And then there's a wavelength dependence here, which is parameterized as an interstellar extinction curve. And so if you look at the flux versus wavelength, you have an unreddened star might look like this, and a reddened star might look like this. And so wavelength is increasing in this direction. So blue, red, right? And so you have a stronger extinction in the blue than in the red. And typically the way you would measure an extinction curve would be by comparing spectra of sort of pairs of stars which had identical spectral types, which were determined by the absorption lines. So, for instance, two B8 stars, and then you would look at the ratio of these two things, and the ratio would give you some extinction due to dust along the line of sight. And so in this way, generally people divided the optical depth into a constant portion, which was related to the number of dust grains along the line of sight, and then a wavelength dependent extinction function, which was more or less the same for most nearby sources. Now, the exact form of this thing fundamentally depends on the dust grain physics, but we don't really know the dust grain physics so well. And so there's some differences in uncertainty there. And when you look at various lines of sight through the Milky Way, people found that there was a decent universality of this extinction function, which suggests that the distribution of grain properties, basically the composition of sizes and the composition of the dust grains, so the sort of relative composition of silicate and carbon and iron and so forth, and then the sizes of the dust grains were relatively uniform within our local portion of the galaxy. And so they were similar in most lines of sight. Now, this universality is not really exactly true. And so there are interesting variations in universal law that come about when you look at very specific regions, like say the galactic center, or the LMC, or the SMC, or particular star forming regions in some cases. And so basically there's a sort of convention of UV to near infrared expression for this interstellar extinction curve, and typically you can express it in magnitudes, AV, and then you can normalize this in terms of a color access. So EB minus V is a color access between the B filter and the V filter, and this expression of this extinction going from B to V could also be articulated as the extinction in B minus the extinction in V. And this gives you the color term, which is shown here. So those are sort of equivalent. This all assumes that we're talking about things in magnitudes, and hopefully you guys have been introduced to the magnitude system already and kind of have some understanding of it. But effectively, we can sort of say that a magnitude at a given wavelength is equal to the intensity at a given wavelength in log scale plus some arbitrary 0 point, right? And so this absorption coefficient is effectively the magnitude that's actually observed versus the unabsorbed magnitude that was emitted. And so the AB here would be the absorption of magnitudes in the photometric B band, so roughly around a wavelength of 4,300 angstrom. And then AV would be the absorption in the V band, so about 5,500 angstrom. And so in particular, some extinction at a particular wavelength is going to be the difference between the observed magnitude and this unabsorbed magnitude here. And the fundamentals of this kind of depend on the photometric system, whether it's a Vega or whether it's AB. And that reminds me, you need to specify the magnitude system for your homework, which should be AB, but I will send out an email after class about it. So following this sort of nomenclature, we have a simple absorption. So our radiative transfer law here with an optical depth, we can convert this to a monochromatic extinction in terms of A lambda. And so A lambda, it could be defined as 2.5 log E times tau, or roughly about 1.09 times tau. And so there's a pretty good relation between these two. The standard interstellar extinction curve is then normalized in terms of EB minus V. And so you could say the extinction at any wavelength minus the extinction in V divided by this is equivalent to the color term in this wavelength minus V divided by the color term, the extinction in B minus V. So this sort of extinction curve has a universal form, and then there's sort of a simple relation between this selective extinction, EB minus V, and then the total extinction at a given wavelength, EV or EJ or what have you. And so conventionally, you can define how this is related, and essentially this extinction, the interstellar extinction curve, by looking at the ratio of, say, AV to EB minus V, and this is known as this parameter RV, which is the ratio of these two. Now, typically, RV, when we look in different regions of the universe, we find RV can range between a value of 2 and 6. And so often, typically people will assume one of two values for the extinction law to be more sort of universal. And so these typical values are an RV of 3.1, which is very typical of the diffuse ISM in the Milky Way, which is what we mostly observe. So you're pretty safe taking this value here. However, RV of 5 is sort of typical of very dense molecular clouds. And then RV could be somewhat different depending on if we're looking at a very low metallicity environment or a very high metallicity environment. And so generally, this is sort of a consequence of the different dust grain distributions in sort of high NH versus low NH. This NH is just column density of hydrogen environments, right? Or the presence or absence of ices, presence or absence of certain types of grains, and so forth. Another factor here is that supernova are thought to be a good or a potential site of formation, as well as AGP sites. And so dust grains, the formation of lots of dust, in particular dust of a very particular type, might be found near these types of sources. And so that might affect R a little bit. As I said, or hopefully, as I said, R is an empirical factor, and we don't really understand the physics behind it yet. We just understand that there's some variation here. And in fact, we'll see in a second that the variation is a little bit more, how should we say, spectrally structured as well. And so RV here is basically a measure of the slope of the extinction curve. And so a larger RV means a flatter extinction curve. And by extinction curve, this is what I'm talking about. So we can parameterize, this is inverse wavelength here. So it's 1 over wavelength, or 1 over micron. And then this is the ratio of this extinction at this wavelength versus an extinction, say, at I band. And so you can look up these curves for a variety of different sort of relations. But the point here is that there is some variation, and that variation is encapsulated in this R here, or conversely in AV divided by this extinction of B minus V, the selective extinction. And so the point here is that for R of, say, 5.5, you have a very flat sort of ratio here, where this ratio doesn't change much, over this wide range. To give you some sense of, this is the optical range here, which is a zoom in of down here. This is mostly the ultraviolet range. So you can see there's a huge range, or a huge variance depending on what value you choose for R in the UV, whereas an R of 2.1 or R of 5.5 in the optical, there's very little difference. Although there is a slight difference. And then these things actually come back together here and here. And this is the infrared, the near infrared here. And this is starting to be the blue the blue band here. So as RV goes to infinity, the extinction curve becomes very, very flat. And so all lambdas are considered to absorb equally, and this is what we call a gray absorber. And so small values of 3 to 5 typically demonstrate that the interstellar dust is not gray, right? Is not flat. And so this is between, this blow up here suggests that there's a pretty universal scaling, where the extinction at a given wavelength is going as lambda to the -1 or up to lambda to the -1/2. There's some curvature here, but that's typically the form of this. And so if you vary the normalized extinction 1 over RV, this measures the slope of the extinction curve. And you can see in particular that there are very strong variations in the high UV, the hard UV. There's this interesting bump here, which I'll come back to, which seems to have some relation with the R value selected. And then there's not too much difference in the alpha. More generally, and so this is now not the ratio of these two things, but it's just the extinction per magnitude as a function of wavelength. You can see that there's a huge extinction in the UV, right? When in the optical there's relatively low extinction, and the infrared there's no extinction. And so this is sort of the very typical properties of dust. And so between about 7,000 and 3,000 angstrom, you generally have a very simplistic model where you can roughly estimate it based on the slope of something like this. Then between about 7,000 and 8 micron, the extinction law is just independent of RV altogether, or almost essentially independent. Right? So that's this regime here, down here. Below 3,000 angstrom, you have a huge sort of variability on RV with this 2,175 bump and the slope and the curvature distinction all being very strongly related to RV. And then below about 800 angstroms, you have a very steep drop in the UV extinction as you go to the very hard X-rays. And in fact, what's happening here is that the UV isn't really seeing the dust grains as much as seeing the individual particles within the dust grains. And so because there's so few of them, the cross-section is relatively low, and so it starts to go down as you go through the X-ray. Okay, I'm going to stop here for a second and see if you guys have any questions. You've heard all this before? No? Okay. Okay, so those are the broad strokes of sort of how we characterize it and how we deal with it, at least in terms of being able to correct for it. Now, actually getting models of this extinction curve and having it based on very specific grain misters, this is possible, but it's degenerate in some levels. And so generally you have sort of, you can pull out a standard interstellar extinction curve, which is determined empirically from spectroscopic measurements of both obscured and obscured sources, obscured and unobscured sources, which are thought to be the same intrinsically. And so this just gives an example of a few of the modern calculations of the extinction curve from empirical estimates. And so there's one which is by Cardelli, Clayton, and Mathis, which is a UV visible near infrared extinction curve. And this is sort of tabulated for our RV of 3.1 and 5. And the tabulation of these extinction curves for these particular RV values is published in Mathis, the annual review article here. Then there's a general prescription that's outlined by Fitzpatrick. And this is actually shown in Bruce Drain's article, which is this previous figure. So these curves here come from this Fitzpatrick sort of characterization of prescription. If you go back in the literature, very often you will see people who, this was only 20 years ago. And so you will read papers where they've made a correction based on a different interstellar extinction curve, such as the Seton law or the Savage and Mathis law. And if you're just thinking about the first approximation, they generally agree, things haven't changed too much because, mostly you're working in this regime here and there's not a huge difference. But there are some subtleties, and one needs to sort of, if you really want to do precision photometry, you need to take those into account. And it's not necessarily easy to do because often people will have published the corrected values, not the observed values. And so you need to be very careful when combining extinction corrected photometric data across large timeframes, because it often has been done differently, and you will introduce systematic errors based on that. And so, a necessary action exercise is you basically have to convert all the data to a common extinction law. And this is also a good reason why it's sort of important to publish your raw data, so that people can correct things with their own methodology, particularly because the knowledge and fashions change, and what you want to do in terms of a correction might change. Okay, so coming back to the 2,175 bump. So this is the dominant feature in the UV portion of the extinction curve. And generally it's in addition to an absorption sort of being proportional to lambda to the -1. And this is in particular a function of what grains are actually in the medium doing the absorption. And so there's some set of carbon, oxygen, magnesium, silicon, and iron that combine in certain grains that produce this bump. And so generally the bump is attributed to carbon-rich particles like graphites or hydrogenated amorphous carbon grains or aromatic forms of carbon. And so these are complex enough that models have a difficult time producing the right level of the bump, and in particular the width of the bump, and the central wavelength of the bump even. And so we're just not to the point of being able to model this, which is a pretty fundamental feature of this. So this model here is just an empirical sort of estimate of that. But if you look in any particular line of sight, you might have variations in this bump, which are an important characteristic if you're looking in UV. And so this is a strong function of metallicity, which makes sense because you need metals to form some of these carbon-rich particles. And so the bump actually gets slightly weaker when you look at the LMC extinction curve, which is about 40% solar, and it disappears almost entirely in the SMC extinction curve. And I'll show you, I think I'll show you some examples of those later on. So that's this bump. Another interesting feature is something called diffuse interstellar bands. And these are bands of about 100, 150 angstroms or so. So they're pretty broad. And they're absorption bands in the visible portion of the spectrum. And they were discovered 100 years ago. And there's about something like 100 of them known now. Yet no one really knows exactly what produces them. And so they only have sort of provisional IDs of these things. And so this is an extinction curve, and you can notice these bumps here and with these different wavelengths with different widths. And so these are all of the interstellar diffuse bands, and the extinction is going up, right? So that means there's higher extinction at these bands. But no one really knows why these are produced or what's producing them. And so the broadness of the bands ruled out sort of molecules with fewer than 5 atoms. So they have to be relatively complex, but again, no one has really been able to identify them. The strongest diffuse band is at about 4,430 angstroms. Moving into the mid-infrared, you have a couple of very strong features which come out in either absorption and sometimes in emission. And so one feature is this aliphatic CH feature. So these are from this is a CH compound of ethane or isobutane. And so these are not too complex molecules, but they produce a broad feature at about 3.4 micron. So this is the spectrum at 3.4 micron. And this is a laboratory measurement, and this is a measurement of various, I think this is a star forming region. This is the galactic center. And so you can see that this feature here in this, it's this absorption and then possible emission feature here is decently produced by the laboratory analog. Of course, these are simple things, so it's not too hard to reproduce. But then, when you look to the galactic center, it's more complex. And sort of understanding what is making this. And this is thought to be sort of hydrogen processed carbon in particular. So these are, what's happening is you're getting a stretching mode of these aliphatic hydrocarbons. And the origin of these and exactly how you're producing them is not really well known. And so you may have sort of UV photolysis of ice mantles on grains, and then they sort of pop off and make these hydrogenated amorphous carbons. Another feature is the mid-infrared silicate band. And these are features, really strong features at almost 10 micron and 18 micron. And this feature at 9.7 micron is due to silicate oxide bending and stretching modes in silicate minerals. And this is fairly secure understanding of what this is, although how it relates to the column density of silicate oxide is not really that well known. And so this is relatively a featureless band. It's a pretty wide band. I think it's maybe almost like a micron wide. And generally this sort of band is featureless, whereas like laboratory silicate crystals show pretty strong features. And so this is tricky to sort of understand what's going on here. And such that basically astrophysical silicates are primarily an amorphous version of silicate rather than a crystalline version. The feature at 18 micron is thought to be from silicate dioxide. And so you have bending of these two bonds. And again, this is a fairly secure ID, but again, the understanding of it is not super well known. There's another feature at 11.3, which is seen in the dust envelopes around carbon stars. And it's thought maybe to be from a silicate's carbon stretching mode. Then you have interstellar ices. And so there are a variety of ices, water ice, or you also have CO ice, you have carbon dioxide ice, you have methane ice, you have ammonia ice, so forth. And so these are sort of, ices being somewhat crystalline structure of some sort, but not necessarily a very structured crystalline. And so they show up, the major features show up at like 3.1 micron, 6.1, 6.8, 15.2, and so forth. In general, these are icy mantles that encase dust grains, so they're dirty ices, and that makes them a little bit tricky. And so ice mantles are not found on dust grains in the general ISM, but in certain regions of molecular clouds more than anything else. So for instance, the Taurus dark cloud shows water ices. But the water ices are only seen for extinctions along the line of sight of greater than 3.3. So you need certain conditions to form these water ices, or ice mantles. Yeah. So this is kind of what this looks like. This is the mid-infrared spectrum of, I think W33 is a molecular cloud. And so you can see this very strong silicate feature at 9.7. Here's this other silicate feature at around 18. You see some ice from carbon dioxide, from CH4, CH3, water, and this XCN feature, and so forth. So these are all ice mantle features that are somewhat narrow compared to the silicate. They're still pretty wide in terms of, they're still 1.5 or 1 micron wide. And so they really make modeling the mid-infrared continuum a complete pain in the ass. So you have really hard time depending on exactly what portion of the spectrum you have. If you only measure from here to here, you're not going to be able to measure the continuum very well at all. Whereas if you measure around 6 micron, maybe this is actually true continuum. And so it's not a bad estimate. Another feature which is often seen in the mid-infrared is polycyclic aromatic hydrocarbons. And so these are, let's say, narrow. So the strongest pH features are at about 3.3, 6.6, 6.2, 7.7, 8.6, and 11.3 micron. And so there are also weaker features. And so this is just showing mid-infrared spectrum. These typically show up in star-forming regions, and they're thought to be sort of due to processed molecules and dust grains by sort of a UV radiation field of some sort. So you see them in planetary nebula, H2 regions, reflection nebulae, young stellar objects, and so forth. But they have to be relatively dense regions. And then there's some unidentified sort of portions as well. So you can see that they're relatively broad, and they can dominate over the continuum in some cases. And this is just looking at some of these PAHs. So you have coronine, circumcoronine, hexabenzocoronine, and so they're really complex molecules now, right? With some sort of built-in structure there. And so something like about 5% of the total dust grain mass in the Milky Way is attributed to PAHs. Moving to the X-rays, you can also see X-rays, or you can also see the imprint of dust grains on X-rays, and this is mostly from the atomic elements within the dust grains, but they do help or do provide an important source of absorption and scattering for X-rays. And so although the X-ray photon sees the dust grain as a collection of basically just a dense cloud of atomic gas, the energies along the edges can be strongly affected by whether the individual elements are in a solid versus a gas phase. And so the fact that they're in dust, a solid phase, will modify the absorption, the photoelectric absorption edges, blur them, bend them. And so this has, if you had high resolution spectroscopy, which you can have with Chandra and with XMM, and eventually with several new instruments being launched in the next many years, you can see edges of carbon, oxygen, iron, magnesium, silicon, and these sort of change. And so this is a nice way of actually constraining what portions of elements get sort of bound to dust grains and are sort of locked out of the overall ISM. So it's an important sort of complementary feature or way to understand what's in the dust grains. One of the other interesting facts is that the dust will end up scattering the X-rays, and so you have a characteristic scattering angle, which is related to this wavelength and this factor A here. And so this is roughly about 800 arcseconds, and A is the size of the dust grain. And so you can kind of compare models and look at how this might actually affect. And typically you see this with sources that are flaring. And so if you see a source that flares, then that light path is moving out and you can see it sort of scatter. So that's what's shown here with one orbit, and then the second where there's a flare, and then the second orbit where you see that this is concentrated and then it moves out further, and then the flare is gone and you no longer see the dust grains. And so you can track this as a function of time. And this allows you to estimate the dust grains, the size of this and the density and so forth. There's also something called the extended red emission, which occurs between, of course, in the red band, so 6,000 to 8,000 angstroms. And this is near some nebulae, and this can contribute pretty strongly to the I-band flux of the diffuse emission. And this is thought to be due to photoluminescence. But there's not a clear, obvious identification yet. If this is, it's probably some carbonaceous material, but there's no clear sentiment about if it's a PAH, a tiny silicate, or carbonaceous grain, etc. There's, of course, the thermal continuum, which is a very big portion of where the reprocessing happens. And so the thermal continuum from dust takes two forms. And so you have the far infrared portion, and this is typically continuum that arises from normal sized grains that are heated to temperatures of 20 to 40 Kelvin or so from the ambient radiation field. And normal here means sizes greater than about 1/100th of a micron. So this is about 100 angstroms or so. And then you also have a portion of this is from cooler cirrus emission. So these are grains that are in equilibrium with the interstellar radiation field. And then you have warmer dust, which is associated with star clusters and star-forming regions. So you can actually pick this apart in a little bit of detail into hotter and cooler and larger and smaller dust grains. Then you have the mid-infrared to near-infrared dust component, and this is from non-equilibrium heating, right? So not from a isolated or a large-scale radiation field, but from a centralized source typically. And so this is tiny grains that are heated in the vicinity of relatively hot or relatively UV bright sources like stars or AGN, planetary nebula, white dwarfs, etc. So these have sizes that are smaller, by a factor of 20 to 2 or so of these. And then they reach temperatures about 100 to 1,000 Kelvin. And so in general, this dust continuum, one might naively think, oh, okay, it's thermal emission, sort of crudely constrained by a black body, but actually a black body doesn't fit this very well. And so it's better modeled by a modified black body, where the wavelength dependent emissivity was going to go as lambda to the -1 to lambda to the -2. And this means that the Rayleigh-Jeans portion of it is not new to the -2, but it's something a little bit shallower. And then finally, you have dipole radiation or dipole radio emission, and this is from grains that are spinning. And so rather than having a molecule like CO, which is spinning and gives you an emission line, because the molecules are more complex, you get a band. And these are thought to be spinning charged dust grains, and they emit both electric and magnetic dipole radiation based on this. And so the grains will spin due to thermal and subthermal processes, and they get charged over time by interaction with the UV photons in the interstellar radiation field, and they'll eject electrons from the surface. And then this leads to a dipole on the molecule, and then you are spinning and you get dipole radiation. And the characteristic frequencies are typically between 10 and 100 gigahertz or so in a millimeter band. So this is just showing you all of what I just mentioned. So this is the far infrared dust portion, right, which is sort of modeled here. Looks kind of like a black body, but this component is not a Rayleigh-Jeans slope necessarily. And then you have the warm component, or the small dust grain component, and you have emission lines here. You have a continuum, and it's much harder to model, right? It's not just a exponential drop off like a black body would be. And so in terms of the total power, if this is the observed emission from interstellar dust, if you sum it over the sky, and so roughly about 65% of the energy comes out here, 14% comes out in the mid-infrared, and then 20% comes out in the sort of mid to near infrared. And then this sums to sort of the total power, which you would estimate as the bolometric sort of luminosity of the galaxy. And this is given as a function of the intensity divided by the column density, the equivalent neutral hydrogen column density. And so this assumes some sort of abundance ratio to neutral hydrogen. This is in the radio between 10 and 100 gigahertz. This is the radio component here, this dipole radio emission from spinning grains. And you can see that the constraints are not too good. This is from dust. This is from synchrotron radiation. This is maybe from free. And so there's this extra bump here, and it's not really fully understood exactly what's going on here. But it seems to be in excess of what would be there for free emission because of this sort of bump character. Okay. Any questions?
I have a question. Well, I have two questions. The first one is, I was wondering if, in fact, at the end, these extinctions law are totally independent of the source that illuminates the grains, the dust grains.
At which wavelengths?
At every wavelength. I mean, I'm not sure if in order to, it's in relationship with the second question, and the question is, it's not clear for me how the extinction curves are building in different systems. So I don't know if, for example, they assume a specific source with a specific radiation field with a specific shape of the spectrum, and then they estimate the absorption, or how they can
well, so for instance, one way of doing this for the diffuse ISM from the Milky Way is to just spectrally type stars based on spectroscopy. Right. And so there you go through and you say, oh, this is a B star, and we can figure out, okay, it's also, got a certain width and a certain surface gravity, et cetera. So we can compare like sources. And then you can say, okay, well, the line of sight column density of hydrogen based on radio data, radio emission, for instance, or radio absorption, which we studied a couple lectures ago, you can relate that to the extinction along that line of sight for that particular star, right? So you can take a star which is unobscured, completely unextincted, and then you can extinct it by a certain amount and compare it to the colors, the photometric colors or the SED of the star along this line of sight. And you can relate, roughly speaking, the extinction in terms of AV or in terms of A lambda to the column density of hydrogen. And you could also characterize that particular region with a certain R, RV, right? So you could say, okay, along that region is 3.1. And so in that, it's all built up empirically. And so you could also do this in other regions. You could point it towards the SMC, and you can do the same thing. You can point it towards the LMC. You can also do a characterization of galaxies that might be in different regimes and try and characterize what the extinction level should be with this parameterization. And so, and then again, come back to something which you're familiar with, which is just doing an energy balance and saying, okay, does this make sense in terms of the amount of extinction I'm getting in the optical? Is that consistent with the, that's the amount of radiation that's absorbed? And then am I seeing that coming out in the infrared in terms of a bolometric luminosity? Right? So you can do a balance, energy balance to also get at it. And so people have gone through various ways of doing it, and it's a non-trivial, highly degenerate problem. And so you kind of have to suffer through that a little bit because we don't have fundamental physics to demonstrate what this should be. I don't know. I'm not sure if that really answers your question or not. But so to come back to the first portion of it, there are regions where you will get differences, whether it's due to the sources you're looking at isn't necessarily the same as it due to the conditions around that source, right? And so you need to take into account, where's the dust, most of the extinction coming from? Is it local? Or is it along the line of sight? And if it's along the line of sight, then it's okay, mostly Milky Way or intergalactic medium. But there's not much dust in the intergalactic medium. There's not much anything in the intergalactic medium. And so the big terms are typically local to the source and local to us, meaning the Milky Way.
And I have another quick question.
Yeah.
For me, it's not completely clear why X-rays are important. I mean, we have the infrared spectrum that part of the optical that contributes or are affected by the dust. Then in the UV there is not absorption or is scattered from dust, but again in X-rays the spectrum becomes important. And I don't understand very well why in X-rays again is important the absorption, and there is interaction with the dust grains.
Well, again, the X-rays see the dust grains only as a collection of atoms. What atoms in a solid versus atoms in gas. That's the only difference. Right, so they see the individual atoms in the dust grain as they pass through it. Does that make sense? There are quantum mechanics in solid state physics, right? And it's basically that. It's if you pass an X-ray through a crystalline structure, right, you're going to get diffraction, you're going to get things that happen because of that structure, which is different from if you pass it in a gas with silicon. And so it's sort of a similar thing, but it's the minutia of macroscopic processes in quantum mechanics. It's that realm in between there. Yeah. Okay. So in terms of the properties of the dust grains, we can characterize them by having a radius and of course a composition, but we can think of the dust grains as being semi-spherical, having a radius A, and then we can define basically a geometric cross-section and an effective cross-section. And so the geometric cross-section is super obvious, right? It's just pi squared. The effective cross-section is, there's an extra factor here, which is the extinction efficiency. And so this kind of folds in, you know, some sort of slightly quantum mechanical nature of the likelihood of interaction given the size of the dust grain. And so this extinction efficiency for this dust grain is partly dependent on the index of refraction, which here is labeled as U. And this has real and imaginary parts. So it looks like our normal index of refraction, but then there's a imaginary component as well. And so typically the real part is large, and the grain is then, you know, if this real part is large, then the grain is really an effective scatterer. And this is true for dielectric or icy grains. If the imaginary part is large, then the grain is an effective absorber. And this is true particularly for metallic grains. And so you can parameterize this in terms of, you know, the grains in terms of the size of the grains by a dimensionless parameter, which is based on the size as a function of wavelength, the incident wavelength that's coming onto or interacting with the grain. This is a very classical treatment, right? And so this is a treatment of light and EM waves as opposed to discrete photons. And so here you kind of enter into a semi-classical treatment of how you deal with the interaction of grain and photons. And this is particularly when you're considering non-equilibrium heating of tiny grains. So we can think about the optical depth, and that is going to be a product of the dust grain column density and the absorption cross-section. So this is the column density, this is the geometric cross-section, and this is the this extinction efficiency. And so that equals tau. And so remember, we had this relation between A lambda and tau, and so we can relate this to the number, the column density. But we need to know something about this and something about this to estimate that. And therein lies some of the problem. And so if you can define some of these, you can get out some of the other properties. Okay, so right, as I said, this extinction, we can divide it into a scattering and absorption component. So total extinction equals scattering and absorption. And the scattering portion of this can be considered the albedo of the grain. And so we can define an albedo, which is this, which is the cross-section for absorption divided by the total cross-section. And so this is equal to this sort of scattering component and this extinction component. Is that right? I feel like maybe I got this. This should be scattering. I think that should be scattering. Hold on. Oops. Let me edit that real quick. Find that I got it wrong somewhere. I think that I screwed that up. Okay. And so the point here is that there's also an angular dependence on the scattering. So the orientation is potentially important. And so dust grains tend to be strong forward scatterers. And so this is, if you have a detailed dust model, this needs to be factored into that. And so the scattering, what we call the phase function, is this, basically is the average of cosine theta. And so this is if you integrate over all of the solid angles, you end up getting out something which the intensity as a function of angle is going to be proportional to cosine theta, where this cosine theta, if it's 1, it's all forward scattering. If it's 0, it's isotropic. And if it's -1, it's backscattered. And so for icy particles, the scattering is greater than the absorption, but the absorption is greater than 0. And so generally speaking, even if you have a very strong scattering component, aka a high albedo, there will be some absorption of incident radiation, which ends up heating up the grains. And this means that there will also be some emission, some thermal emission that comes out. And so we have a couple of different cases that we can think about. One is a long wavelength case, and so a small x, or basically that the wavelength is much larger than the grain size, grain radius. And this reduces to classical Rayleigh scattering, which we talked about before. And so generally speaking, you can simplify this if you say this is a dielectric sphere with no absorption, then this thing is fully equal to the scattering. Or this isn't exactly true, strictly true, but it's close. And so this goes as 8/3 x to the 4th, and then the real portion of this quantity here. And of course, this is then proportional to wavelength to the -4. And then in this regime, the cross-section ends up only depending on the mass. And so this cross-section here is generally proportional to this quantum efficiency, or this, sorry, Q efficiency, times the fundamental or the geometric cross-section. This is proportional to A, and so this is proportional to A to the 3rd, and so this is proportional to the mass of the dust. In the short wavelength case, we can also fall back to classical limits, which are my scattering. And so here we can consider a pure scattering case again. And in this regime, we have an index of refraction of 1 to 2. And so the extinction is, again, if we have a low absorption case, the total sort of Q factor here is basically equal to the scattering portion of it. And this is going to be equal to this complicated thing here, where this thing is now related to our value of x. And so this thing is equal to 2x times our complex index of refraction minus 1. And so it's not trivial here, but you can kind of get the correct behavior. The point here is that this extinction factor here is sort of oscillatory. So it has cosine and sine terms. And so it looks something like this as a function of x. And so you get certain wavelength regimes where you have higher or lower extinction efficiency. And this sort of gets it, sort of is in a band like structure. And so generally speaking, as x becomes very, very large, this will sort of asymptote to 2. And so it goes something like that. But for different complex indices of refraction, you can see different behavior is sort of the point. And so in this limit, basically the dust grain acts like a macroscopic opaque spherical ball. So the location of the first peak depends on n, and then there's this resonance between the incident light and the particle dipole moment. And so in classic my scattering here, the grain size shows a sharp rise at long wavelengths, or the scattering curve for a fixed grain size shows a sharp rise at long wavelengths, and then it flattens out at short wavelengths. And this is kind of just this, it's showing this sort of dependency. Okay, and so broadly this is saying that there's, what we're ending up seeing is actually that there's a distribution of sizes of particles. And so we see a relatively sort of flattening at short wavelengths, which suggests that there's more small grains than large grains in the ISM. And this gives rise to the observed scattering curve that we see, or the empirical one. If we were to allow the grains to have a finite absorption term, then generally speaking, this absorption should be larger than the scattering. So, effectively what we're saying is that the imaginary part of the index of refraction is non-zero. And so at long wavelengths, the absorption will end up dominating. This absorption term, as I mentioned, this is the imaginary part, and so this absorption term goes as something for x here in this sort of grain divided by wavelength, and then the imaginary portion of this, and this goes as lambda to the -1. And so we can recall that we roughly were saying that this extinction is roughly proportional to lambda -1 in the optical and the infrared portion. Right, so when I was saying that AV roughly went as lambda to the -1 in the optical portion, we're in the Mi scattering regime. And this is effectively why it has that shape. Now, if we look about it, we were talking about kind of very basic cases, and so if we think about more complex cases, so pure versus dirty dielectrics, then you end up with these sort of resonances here that are on top of this as you go to higher wavelength, or sorry, lower wavelength or higher X. And this is with 0 term here for I. This is with 0.5 in the complex portion. You can see sort of what happens versus this. Right, for the same index of refraction, the real portion index of refraction. And so you have a portion which is scattering, which is, and then a portion which is extincted here, and there's an absorption term that's coming in. This is a function of the angle, and so this shows the angular dependence for different x's, different wavelengths, or different grain sizes. And so this is the intensity parallel and perpendicular. And so the parallel is in solid, and I think the perpendicular is in dotted. And so you can see really strong dependencies on what the intensity is particularly for, this will be small grains or long wavelengths. Right, which make a small x. And then for short wavelengths or large grains, you generally don't have, it becomes a very strong forward scattered component. These are some model curves. These are now in terms of albedo and in the scattering angle for different regimes. So diffuse galactic light, molecular clouds, or reflection nebulae, as a function of inverse wavelength now. And so these are dust models for these different regions. And so you can see that the albedo changes, and these are the models versus the data. And so, okay, not bad, but not good either. And so this is kind of state of the art, right? Or at least 10 years ago, state of the art from Bruce Drain. And so you kind of get the angles right, but you don't quite get the albedo right. It's complex. And so there's just a lot still needed to be done here to understand the complexities. But generally speaking, the albedo is about 0.5 from the visible to the UV. And the grains are generally forward scattering. So this factor is about 0.6, right, which is sort of shown here. And so the observational lengths are, I would say, very broadly to 0th order consistent with the dust models. Then a couple of interesting sort of side notes. So this is what you can kind of do with, once you know and understand dust and dust scattering, you can use it to, for instance, find light echoes from supernovae that have gone off, in this case, tens of years ago, but you can actually look in the galaxy and find supernovae that have gone off hundreds to thousands of years ago. If you look over large enough areas, and LSST will be able to deliver some very interesting results on this. This is another movie showing the Crab Nebula, and this is in polarized light. And so showing how the dust in the greater sort of regime are being tracked by this. This is dust along our line of sight to some extent. So you're able to see both effects there. And then this is dust scattering in the X-rays. And so this is actually a dust scattering sort of shell. And this is, you can see this is in now, I think this is in intensity, and this is just showing sort of the extinction that you would get. And I'm not going to go through this in too much detail, but this kind of goes back to Laura's question about what the X-rays see. And so you can see, I think I showed you before the extinction curve here for gas, ISM, which is shown by this curve. And then this is the extinction curve from dust, and this is the scattering from dust. And so you can actually see that dust makes up an important component. Now this is cross-section. It's not the total, you need to divide by the number density or whatever to really get at how important the dust is. But it's potentially important at high energies. And this is the angular dependence of this as well as a function of energy. Yeah, one critical thing to sort of note here, and I mentioned this before, is when you're trying to calibrate all of this, you have a visual extinction at some wavelength, and that's typically along the line of sight from the ISM. And you also typically have a column density of hydrogen, which you've measured from the radio telescopes, from the spin flip. And so you can relate those. And crudely speaking, this ratio in terms of A to the I or A to the V is roughly about, well, in this sort of nomenclature, and this I think has to be wrong because this is 2 to the minus 25 and this is 2 to the 21. I think, okay, I see, yeah, this is divided by this. So, okay, yeah, so roughly speaking, these are a factor of sort of 1.5 between each other. This has an RV term in here, so you can plug in your RV term. This does not. But roughly speaking, for the Milky Way, AV and NH are roughly proportional in this regime. And so you can use this to kind of estimate what AV you should have based on their all-sky surveys of NH. And so you can look at a given line of sight, plug in your NH and get a rough AV estimate for that line of sight. Then we have the gas to dust ratio. And this is, so this is kind of related to the gas to dust ratio. But generally speaking, the gas to dust ratio can be estimated. And this is a sort of way to estimate it. So taking the AV as a function of wavelength divided by the luminosity, and then you can estimate the number density of the overall density of dust grains and the volume that they have. And so this number of dust and the volume will be equal to the density of dust divided by the density of all grains. Is that it? Let's see, I think I have that right. And so this is the spectral average dust density, and this is the density of each grain. And so this thing here is the individual grain mass, and then the luminosity is whatever is along the line. I'm sorry, this is not the luminosity, this is the distance. L is the distance. And so the idea is you actually can start to understand the composition of the material that's affecting your overall extinction. And so you can plug in different values of your grain masses and so forth. And so the idea here is that you can use this sort of estimate of understanding the mean density of dust, and you can then compare that to the mean density of gas, which you can measure from NH. And so sort of plugging all this in, you have this density of dust to gas is related to this integral over all wavelengths divided by the number density of, or the column density of hydrogen. And then some estimate here of the density of a grain, the mass of a grain, and whatever complex index of refraction you want to assume. But nonetheless, you can kind of get out this, or if you have this, you can start to understand a little bit more about the properties of the material in the ISM. And so for silica grains, we could plug this in, and silica grain has an index, a real index of about 1.5. It has a density of about 2.5 grams per cubic centimeter, and we can plug in the empirical extinction law here for the ISM. And so you can estimate that roughly the gas to dust ratio here is about 19 times this divided by this. Remember, this thing was between a lambda of minus 1.5 and minus 1. And so you could estimate that the dust to gas ratio is about this. And so if you assume here that the UV contributes another sort of 50 to 100% of the total sort of contribution to this thing, you might end up with, or sort of, rather that you're not getting everything, and that the UV is only contributing sort of 50 to 100%, or rather, sorry, between, yeah, there's a UV portion and then there's an absorbed portion. So we're only seeing sort of half a portion of that. And so basically, if you combine the different estimates and account for everything, you know, the estimate just from this extinction is about 0.04, and then you get another contribution which might double it. And so generally speaking, that this is kind of consistent with what we know about the observed depletion studies, which estimate a dust to gas ratio of about 0.06. So things kind of work out, is the point. I think that's all I really wanted to say. There's a lot there, but I just wanted to introduce this so you kind of had some idea of where to go and understand what's going on the complex side of things. Any final questions?
I've got a question, but about the homework. Okay, so in the second problem, there is a hint that we should differentiate, and I managed to do that. Then when I put the different numbers, I assume that I should get a number for quota. I don't know how to say that in English. For
J.
Quota. J. That should be a number without any commas or point something, since it's a level. But when I put in the numbers, I've got numbers really weird, and I don't know if I should. I don't know. Maybe I'm obviously going to say that 1.999 it's 2. I don't know if I can do that if we're talking about levels.
So I mean, what you will end up getting for the peak is not a whole integer, right? And so then it's between one or the other, right? If you can round it, and you can figure out where the peak is going to be.
Okay. Yeah, that makes sense. Thanks.
Profesor,
Sí.
que la presentación de la clase de hoy día no está en su página web.
Ok. Voy a cambiar todo. Disculpen. Ok. ¿Otras preguntas? Voy a ponerlo allá en 2 minutos.
Existe cosmic dust in a planetary ring?
You mean in a protoplanetary disk?
Yes.
Yeah. For sure. And in fact, they are, as I mentioned in the first slide, they're super important for forming planetesimals. It's mostly, they're the locations where you start to build complex molecules. And so, yeah, you build up material partly based on that. And certainly, I mean, they're the origin of, the complex molecules that we have in comets and, that we have here on Earth. In part, the original primordial versions of those were all made because of those disks and the formation of dust grains or the formation of molecules on dust grains.
Mhm. Thank you.
Anything else? No? Well, I hope that you guys learned something this semester. And you have a better appreciation for all of the things that go into what makes emission, what absorbs emission, what scatters emission. And you can hopefully take at least a portion of what you learned and use it in your more daily lives. And understand the colloquia better, everything, right? Hopefully that helps. Right. Okay, you guys are free to go. Fill out the poll so we can figure out the time for the exam on that week. And I'll also give one last office hour, yeah, on Friday. And I think, did I give a review session last time? I sort of did. So maybe we can organize a review session as well the week before. We'll have to see. Okay, ciao everyone.
Bye. Thank you.
Bye-bye.
Bye.
Bye.
Bye-bye.